So let's have a little more practical use of this stuff where we're manipulating power series. We're going to have something where the goal is actually integration. And so we'll start out with a power series that doesn't involve an integral, and then we'll do a definite integral of that. But we'll just do it as a power series, and we'll use a get approximation. Very like standard examples. So first of all, our starting point is still the geometric series. And so and I'm going to write everything. With this one, I'm going to write it out. I'm not going to use summation notation because I'm going to be interested in truncating anyway. And I'm not super interested in the infinite pattern here because whenever you're doing approximations, you're going to chop something off almost always. Okay, so 1 over 1 minus x to the 8th. That's a substitution one. So that's going to be 1 minus x to the 8th plus x to the 16th minus x to the 24th. Oops. Those powers are getting big pretty quick, and so I'm going to hope that I don't need more. I can always come back as well. Okay, now I'm multiplying that by 1 plus x squared. Okay, so that's a little bit more than just multiplying it by a monomial, but I can do it as, so this is just, of course, just a complicated way to write 1 plus x to the 8th. Okay, whoops, I don't really want that. I want it there. Okay. So if I look at that and I did multiply it just by x squared, that would boost up all the powers by 2. Okay, and now it's just the sum of these two guys. So this is a fairly simple way to multiply by a simple polynomial. Just figure out what it is times the constant term, times the linear term if at all, times the quadratic term. Get all those things together and then just add them term by term. And so the whole thing, I mean, this is really how you multiply, usually like by decimals or something. Just do it in a tableau, multiply by very simple things, and then add the results. So I'm going to get 1 plus x squared. And then the next term is going to be the minus x to the 8th. The next one is the minus x to the 10th. So I'm just adding them and noting there's no overlap, which is kind of special. And then just putting them in order, because that's going to be important when we look at where do we have to truncate. Okay, I'm going to go further than we probably need to go here. Maybe the pattern is kind of interesting. Okay. All right, so now I get to integrate that. So here's the great thing about integrating from 0. If you're doing a definite integral from 0, it's like with a polynomial. You're going to get 0 when you evaluate at 0, so it's going to be a little simpler. Okay, so this is basically integral. Oops, just deleted a space there of this whole stuff. We put in parentheses. Okay. And so, except for the dot dot dot, it's just like integrating a polynomial, and it evaluates to 0 at 0. Well, let me just do one more step. Let's say it's x plus x cubed. Whoa, that's not what I wanted to do. X, not doing too well here. There we go. X cubed over 3 minus x to the 9 over 9 minus x to the 11 over 11 plus x to the 17 over 17 plus, sort of trying to be clever here, a little quicker, 19 minus is 25. Let's just do one more, almost certainly more than I need, but it's a little hard to know in advance. Okay, and that's evaluated from 0 to 0.5. And like I was saying, you usually would have to evaluate it both places, of course, and subtract, because this is a polynomial, and whenever you integrate to get a polynomial, it's not going to have a constant term. It's always going to die at 0. So fairly common situation. Of course, why are we doing this with a power series? Let me just mention. I should have mentioned that at the start. This integral would be a gnarly, like partial fractions kind of thing if you didn't do it this way. And because we're going from 0 to something close to 0, it makes sense to use these power series. If I truncate these things, they're pretty good approximations as long as I stay near 0. Now, one thing I should have done right at the start, just kind of think about other things, I really should have noted where's the radius of convergence of this thing. That is where absolute value of x is less than 1, of course. This is going to converge where absolute value of x to the 8th is less than 1. Luckily, that's the same thing as where absolute value of x is less than 1. And so it's legal to do this at all as a series from 0 to 0.5. And it says that we could even take it out as the infinite sum and make some meaning of it. Truthfully, we're not actually going to take the infinite sum here. We're going to use an approximation. So it's really better to say we're kind of using a polynomial approximation from the start. But if you're going beyond the radius of convergence of the whole series, it's pretty dubious. You'd have to do some extra justification. Okay, so this whole thing, okay, so now we want to start paying attention to what kind of accuracy do we need? 10 to the minus fifth, okay? And I'm going to start writing it down, and I'm going to note what kind of series of numbers we're getting. We have various techniques for approximating things in series, and when you get to Taylor series stuff, if you've seen that before or not, you get some more techniques for estimating error in this stuff. But your go-to one, if you can use it, is the alternating series test. And the great thing about this particular kind of series is this is alternating. That's lovely. And the first place the alternating came in was the 1 over 1 plus something. That's a very nice series, and it's a sign that you might well get something where the signs are going to alternate in your final answer. Okay. Now, it isn't absolutely strict alternation here, because we have, whoa, that's true. This isn't quite strict alternation. Maybe I shouldn't have picked this example. Well, let's see. We can still do it. We want to be a little careful because the alternating series test is pretty strict about exactly what kind of thing you need. So let's take it out a little further, though. I forgot that I modified my example a little bit from my previous one. So, okay, 0.5 to the 11th. We can still salvage it. Be a little more interesting. Okay, these are getting pretty darn small, I think. Okay, so in terms of alternating, this one, the problem was we had alternating. When we put in the 1 plus x squared, it stopped being purely alternating. It was plus, plus, minus, minus, plus, plus, minus, minus. But one thing you can always do, it's legal. You can't do like infinite regroupings. That's totally illegal. But if you just regroup little bits, that is legal. And notice what we're getting. When you group those guys, then it's actually alternating. If you do this sum first, yes. If you do this sum first, yes. As long as it's convergent at all, this kind of regrouping is legal. And this is convergent. We're staying within where we want to be. And it turns it into something that's written as an alternating series. Okay, so now we just need to figure out where is the next term going to be smaller than 10 to the minus fourth. And then it says we can just take everything up to, but not including that. Honestly, you might as well include the one that you just checked, but you don't have to. Okay, so let's see where we got. Let's just start evaluating these. Okay, that's probably worth just doing by decimal. Ooh, you know, this is getting so big. I'm going to take this and I'm going to take it out in a new display. There we go. Okay, so otherwise it starts being weird. Okay, 0.454167. Okay, minus. Ooh, that's already pretty good. I'm going to write it out with decimals. Not scientific notation yet. But you know what? This one. Oh, yeah. Okay. So if we want the minimum amount of terms to add together to guarantee that the remainder is less than 10 to the minus fourth, you just need these two. Because the alternating series test, let me write that down, or the alternating series remainder estimate, guarantees that the remainder, just for those first two terms, the absolute value of the remainder is less than this guy. You can also say that this must be an underestimate because the next thing you would have added is a plus. And so we just need this guy. So we could just say it's approximately this number. Let's evaluate that. And I always like it to go where it doesn't go. 4141. Okay. Now, one of the things about this process is that in order to figure out what this is, you're probably going to evaluate it explicitly anyway, and you might as well put it in. So I would just say, unless it like overcomplicates something you're going to do with this expression, but if with a number it hardly ever matters, I would just put this in, but people won't. Oh, sorry, just want to evaluate that. Oh, and the thing is, I have to get more. I have to have this thing display more decimals to even do that. So in this case, to the accuracy that we were asked for and to the accuracy that this calculator is set for right now, we're actually just not going to get anything more. Okay, but it's not crazy to add this one in if you want to. Okay, that's it.